Welcome back. This is video number 2 of concavity and points of inflection. So we are given this nice table that kind of organizes the information, some of the information that we've already done over here, and then some information that we're about to do over here. But it's written in a way where we can kind of make connections so that we can remember how to do things a little bit easier. So for example, if we're given the first derivative, we know that we can find a critical point by setting that derivative equal to 0 or finding where the derivative is undefined, where it doesn't exist. Because that's going to help us find where the function is increasing, because the function will be increasing if the derivative is positive, and it's going to be decreasing if the derivative is negative, which in turn is going to help me figure out relative maxes and mins, because that's going to help me. I use the derivative to see where it changes signs from positive to negative, or it changes signs from negative to positive for the relative min. So this is what we did in the past. And so now we're going to use the second derivative to tell us something about the function. If I take my second derivative and I set it equal to 0, or find out where the second derivative is undefined, we have possible points of inflection. That doesn't mean that they're automatically points of inflection. We're going to have to check. How do we check? Well, we find out where the second derivative is positive, because that means it's the function, original function, is concave up. We find out where the second derivative is negative, because that's where the original function is concave down. And if the second derivative changes signs, then we know the original function has a point of inflection. So setting the second derivative equal to 0 or finding out where the second derivative is undefined or does not exist doesn't automatically give us a point of inflection, but those will be the candidates for testing to see if there is a point of inflection, and we're going to test it by building a sign chart. And so if you look at the next page, that's exactly what we see on this side. To answer questions using the second derivative, we got to find the possible points of inflection, and we do that by setting the second derivative equal to 0 or finding out where it's undefined, the second derivative. We're going to build a sign chart to find intervals where the second derivative is positive, meaning concave up, the original function concave up, and the second derivative is negative, where the original function is concave down. And then we're going to interpret the sign chart to see what's going on and possibly find those points of inflection. So it's a very similar process. However, we're dealing with the second derivative. It's very important that we label our sign chart so that we know what we're looking at, and always read the question to make sure you're answering the question they're asking. So we're going to start with example 1 here, and we'll finish example 1 in this video. The question is, can you find the open intervals where the function f of x is concave up and where it's concave down? And can you find any x intervals where the function f of x has a point of inflection on the interval between 0 and 2 pi? Give a reason for your answer. Okay, so if I'm talking about concavity, I need to find the second derivative, which means I need to find the first derivative first. So let's find the first derivative. This would be 4x to the third minus 6x squared minus 24x. Great, I got my first derivative. But this would help me if I'm looking for increasing, decreasing, or if I'm looking for relative minimums and maximums. So I'm going to go on to the second derivative. Take the derivative of the derivative. So that would be 12x squared minus 12x minus 24. This is the function that we're going to need to analyze whether we have concave up or concave down in our original function, right? So we're using the second derivative to tell us something about the original function. I notice that all of these are divisible by 12, so I'm going to factor out a 12. And then I know that we can factor this out if we do something like this. I think it's x minus 2, x plus 1. And so there I have my second derivative. Great. Do we know what are the x values that make the second derivative equal to 0? Well, I'm going to write down here the second derivative is equal to 0 if x equals 2 and x equals negative 1. How do I know that? These two x values are the numbers, the values, that if I substitute them into my x's in the second derivative, it'll make the whole thing equal to 0. Is the second derivative ever undefined? Well, this is a quadratic. Quadratics are always defined. They're defined for all real numbers. So these are the only 2 points that I'm going to use to partition, to break up my sign chart. So I'm going to come over here and build my sign chart. It'll look very similar to the one I did when I was increasing, decreasing. I am going to say my x values are at -1 and 2. Please put them in the correct numerical order. And we're going to say the second derivative is 0 at these two x values. But just like before, we're going to need to test some numbers. So let's pick a number bigger than 2, like 3. I'm going to substitute 3 into the second derivative. If I substitute 3 into the first factor, I'm going to get positive. Substitute 3 into the second factor, I get positive. And positive times a positive 12 is a positive. But I could have picked any point on the right side of 2, so therefore all of these would give me a positive second derivative. I pick another point, this time in between -1 and 2, like 0. If I substitute 0 in this factor, I get -2. Substitute 0, I get +1. Positive times negative times positive, that's a negative. But again, any number that I could have picked in that interval between x equals -1 and x equals 2 would have produced a negative second derivative. So I'm going to put negatives throughout. And then I'm going to choose one last one. Let's choose -2. -2 minus 2 is a negative. -2 plus 1 is a negative. And a negative times a positive is positive. So what do we know? We know that the original function is concave up. I usually do like a little u here. It's concave down, and then it's concave up again. So I can say f is concave up on these two intervals, x's that are less than -1 and, or I guess I should say or, x's that are greater than 2. And I know this because the second derivative is greater than 0. Right? That's what we were told. Come back over here in case you forgot. I know that a function is concave up if the second derivative is equal to 0. Is greater than 0. Okay. So I got that. When is the function concave down? F of x is concave down on the interval between -1 and 2. So in this interval, it's concave down. How do I know that? Because this is your justification. The second derivative is less than 0. Awesome. So far, so good. But now, are there any points of inflection? Well, yes. There are points of inflection at x equals -1 and x equals 2 because, let's write out the word, because the second derivative changes signs at those points. Remember, we were told in the first page, I'll come back, I'm sorry if I'm going fast, that if the second derivative changes sign, then I know there's a point of inflection. Well, it did change signs. It changed signs. The second derivative changed signs from positive to negative, and the second derivative changed signs from negative to positive at these 2 points. So that's how I know there's a point of inflection. And that's it. That's what the second derivative can help us with. It can help us find intervals of concavity and points of inflection. We'll come back in the next video and we'll do example 2. I think that one might have been the one that has the domain of 0 to 2 pi. I think this might have been a little bit, he might have put this a little bit early. I think that one maybe goes for example 2. But we'll come back and we'll take a look at that. But we'll practice the process.